Hey everyone, today I'm going to be talking about Fourier analysis. What is it? Well, mathematically, it can be represented by these two equations. However, these require a lot of prior knowledge of calculus to understand, so it's not really useful going over. So let's get into some analogies and some layman's definitions to understand it. First, think of a bowl of soup. That bowl of soup can be broken down into ingredients, which can be listed, such as chicken broth, chicken breast, some vegetables, noodles, maybe some salt and pepper. All those ingredients combined, guided by a recipe, make that bowl of soup. Sound works in a very similar way. When you listen to a song, you're listening to a combination of different notes that come together to form one sound that your brain interprets in that specific way. So when you listen to someone speak or music being played, you're actually listening to a combination of different sound waves that work together to sound the way that it does. So, what does Fourier analysis do? Well, given a wave, let's start with a simple wave, which is a function of time, you can find the frequency. So, function of time means that the wave reacts based on how far along into time it is. An example is when you speak. At first, the wave is going to have a very high amplitude when you speak, but it's going to damp until it's zero after a couple seconds. Now, when you have this wave, this simple wave, you can find the frequency. You know the period is 1 because I marked it. So the frequency, which we know from class, is 1 over the period, is 1 over 1, which is 1. Now what Fourier analysis attempts to do is it decomposes a wave into its frequencies. Given this simple wave, it's very easy, and we can even do it ourselves. So let's try to do it. Essentially what we're doing is we're taking a function of time, x of t, and x of t represents this wave right here, and we are transforming that or mapping that into a function of frequency. Alright, so given a new graph that is a function of frequency, we can have little markers 1, 2, and 3. What Fourier analysis does is it looks at the original wave and it says, are there any frequencies of 0 hertz? In this graph, we know there's not. It's only 1 hertz, so there's nothing from 0 all the way up to right before 1. At 1, there is the frequency of 1 hertz, so yes, there is. Is there a frequency of 2 hertz? No. Frequency of 3 hertz? No. It's only made by one frequency. Essentially, we have just decomposed this very simple graph, this very simple wave, into its frequencies. This may seem really easy, but it gets much more complicated with more complicated waves. Let's look at this example. Sine of 2 pi x is very simple. You can find its frequency, you can find its period, and you can likely map that in its frequencies. Sine 4 pi x is the same exact thing. We know that the period is 0.5, we can find its frequency, and we can do the exact same thing. 7 pi x, yes, we can find its frequency, and essentially we have just performed Fourier analysis. However, when you combine all of these graphs together, you get something much more complicated. Given this graph by itself, it's very difficult to find the frequencies by yourself. How could I go about finding which frequencies make this up? What Fourier analysis does is it decomposes this entire graph into the frequencies that make it up. So this is just an example of how Fourier transform can be used. I used MATLAB to code something very quickly to show how it can break down a function defined by time into a function defined by frequency. So basically, I have a frequency set at 15, and it is in the form of a sine function, and that's going to be transformed using Fourier analysis into a function defined by frequency. So let's see. So as you can see, this is the time domain wave, so the normal wave, and it's very simple, it has a frequency of 15, and on the Fourier transform, it has found and analyzed that this has a frequency of 15, and that's why that's the only point that is above the x-axis. So as I said, that's pretty simple, and we kind of did that on our own. But here's what it does when there's a much more complicated function. So right here you can see a lot of different sine functions with many different frequencies, 5, 6, 23, and 37. What I have done is added these all together to form one larger, more complicated wave, and hopefully Fourier transform can find the frequencies of those. So let's see. So as you can see, this is the time domain wave, really complicated, hard to understand by itself. But on the Fourier transform, it has found that it has the exact frequencies that I coded it to have. 5, around 6, 23, as you can see from this list right here, and about 37. So that's the power of Fourier transform. It can take this really complicated function, just break it down to most simple frequencies. Once I have these frequencies, I can actually draw the sine waves themselves, and you can show the 4 different waves that make this up in their own different time domain axes. So I hope that helped understand this a little bit better. I think it's pretty cool. Now let's talk about the properties. These properties are extremely crucial to Fourier transform, and without them, it'd be very hard to understand. First, let's talk about linearity. In that last example in MATLAB, I showed how you could add up many different sinusoidal functions, and it leads to one wave, and then we can decompose those back to those frequencies. This is what linearity is. So let's take a little example. In that last function, that last wave I showed on MATLAB, you could see that it was the function of multiple waves added together. Let's say sine A plus sine B. Using linearity as one of the properties, we knew that we could decompose that into the frequency of sine A plus the frequency of sine B. However, if linearity was not a property, that means that this would not equal necessarily f of sine A plus f of sine B. That means you could not decompose a very complicated wave, such as the one I had shown, into its frequencies. This is essentially the entire point of Fourier transform, which is why this is one of the most important properties. Now let's go back. Time shift, all that means is that you can take a Fourier transform wave and shift it vertically left or right on the x-axis, and that does not affect the frequencies. Frequency and period. This is also a very crucial part of Fourier transform, and it is how we break down the entire wave into its frequency parts. And now wavelength and amplitude are 2 properties that don't conventionally apply to Fourier transform necessarily. If you have a complicated wave, there is no way to identify the wavelength because it is the combination of multiple different frequencies, meaning multiple different wavelengths. Amplitude also does not apply conventionally because, as I showed, the wave is extremely complicated and there was not one constant amplitude throughout the entire wave. I hope this helped understand how Fourier transform works, and thank you guys for listening.